Hey everyone, so in this video we're going to review some key conceptual ideas about orbit, specifically distinguishing between when we get circular orbits and under what conditions we get elliptical orbits, as well as just a really quick review of Kepler's laws at their most basic. Okay. So we'll start with just circular motion in general. All right. So to get an object to move in a circular path, we need to apply a force towards the center of that circle, okay? Because according to inertia, objects want to keep moving in a straight line at a constant velocity. If we want them to keep turning and rotating around something, we need to keep pulling them inward so that they keep circling around that central point instead of just taking off along the tangent. Right. Now, a lot of times when we're talking about that force that's needed to keep pulling something in so that it keeps rotating around some central point, we'll call that force centripetal force. Now, a key point of clarification that I want to make sure you are 100% clear on is that centripetal force isn't a new type of force. It's not this force that appears when an object is moving in a circle. Centripetal force is actually a way for us to kind of figure out how much force we need if our goal is to get something to move in a circle. Okay, so it's not a new type of force that just appears. Centripetal force gives us a way to calculate how much force we need if we want something to move in a circle. So it's like a target goal amount of force rather than a new type of force that just emerges. So if we want an object to orbit in a circle, if we calculate the centripetal force, that tells us, okay, this is the exact amount of gravitational force we need to maintain a circular orbit. Or if we want to swing something around in a circle, calculating the centripetal force will tell us exactly how much tension force we need to maintain a perfectly circular path. Okay, so centripetal force, not a new type of force. It just allows us to calculate how much force we need if our goal is to keep something moving in a circle. Hope that clears that up a little bit. Okay, now again, that centripetal force then allows us to figure out what that goal amount of force to maintain circular motion is, and we can calculate that centripetal force by taking the mass of the object that's moving in a circle times its speed squared, and again, that speed is directed along the tangent parallel to the radius, divided by the radius. So mass times speed squared divided by radius of that orbital path. Okay. So that allows us to sort of figure out how much we need to maintain circular motion. So let's pull that over now to the idea of orbit. Now, gravity is really good for maintaining orbit because gravity is always attractive, which means that that force is always going to be inward towards some central point. So it kind of automatically takes care of that whole inward force requirement for circular motion. Okay, so again, centripetal force gives us a target goal. So if the gravitational force between two objects, which we can calculate using Newton's universal law of gravitation, is equal to the centripetal force that is needed for circular motion, then we know that this object that we've calculated this for is going to keep orbiting in a perfect circle. If those two equations, when we plug everything in, end up being exactly equal to each other, that gravity just happens to be the exact right amount that we need for a circular orbit. But if we notice, there are a lot of different variables that show up in there that can cause these results to go awry, that can prevent our gravitational force from being equal to centripetal force, right? We can have a primary body that's too massive or not massive enough, or the object can be moving too fast or too slow or not perfectly perpendicular to the radius, or maybe the radius is wrong. Maybe the objects are too close together or they're too far apart. So there are a bunch of different variables that all kind of have to align perfectly to achieve a circular orbit, and that's really uncommon and difficult to manufacture. Okay, so more commonly, gravitational force is not going to be equal to that centripetal force required for circular orbit. Okay, so what that means is sometimes we end up with situations where the gravitational force is less than that target centripetal force that we've calculated. If that's the case, gravity's too weak to keep that object curving around the primary body, and so it ends up drifting too far away from the primary body, and it sweeps out farther and farther away instead of maintaining a nice constant radius. Okay. On the other flip side of that, if we have too much gravitational force, if the gravity between two objects is too strong and greater than that centripetal force, then we can run into a situation where then the object starts swooping in closer to the object and draws nearer to the primary body. And both of those scenarios can ultimately produce an elliptical orbit that doesn't match a perfect circle. Okay. So then just to kind of recap, in a nutshell, if we've got a circular orbit, the gravitational force between our two objects just happens to be exactly equal to that target centripetal force needed for circular motion. If the gravitational force is too big or too small, then we end up with a situation, or at least we can end up with a situation where we get an elliptical orbit, where either our object then starts to sweep too far away from the primary body and we get an ellipse if gravitational force is too small, or if gravitational force is too big, then the object starts to curve in closer to the primary body and again traces out an elliptical path. Okay. Now about these elliptical orbits, Kepler had a few things to say about what those elliptical orbits look like, so let's just walk through that really quickly. So Kepler's first law just says that, yeah, planets follow elliptical paths, and more specifically, if we trace out that elliptical path of a planet as it orbits around, the sun, or whatever primary body it's orbiting, is going to be located at a focus of that ellipse. Which we could demonstrate using math, but for now we're just going to say like, oh, hey, that's cute. Look, it lands at a focus. Sweet. All right. So that's the first law. Second law from Kepler is that planets will move faster at perihelion and slower at aphelion. So when our planets are closest to their primary body, they've got the biggest gravitational force, the biggest acceleration, and so they are zipping around really, really fast. Whereas at aphelion, when they're farthest away from the primary body that they're orbiting, we've got the least gravitational force, the least acceleration, and therefore our objects are moving the slowest during that part of their orbit. And then the third law, we end up with this very fancy semi-major axis cubed is proportional to period squared, but the key qualitative idea is just that bigger orbits take a longer time to complete. And that's pretty much it. All right. Hope that clarifies some of the conditions that produce different types of orbits. And that's all. Good luck.